All right, let's come back to our molecule that we originally showed. And we said this molecule has two carbons that have four different, two sp3 hybridized carbons that have four different substituents, therefore it has two stereocenters. We assigned the stereocenters, and then we drew the mirror image. And we established that we could draw the mirror image, and that was an enantiomer, the whole 9 yards. Well, as it turns out, there's an easier way, in my opinion, to form an enantiomer of a compound. What you can do is simply leave the molecule in place, and to draw the enantiomer, you can simply reverse groups on all of your stereocenters. So here we have two stereocenters, number 1 and number 2. So in number 1, let's reverse two of the groups. Now the two easiest groups are the ones that are above and below the plane of the page. So to reverse that, let's simply swap the H and the OH group. When we swap two groups, we reverse the stereocenter. So let's see if I can remember this. That was number 1, number 2, number 3, and we'll go around this way. And so we said that was the S configuration. If you go back and assign the chemical configuration for that stereocenter, you get an R now. We've reversed the configuration. Now, let's redraw this stereocenter and swap the two groups. Now, H will be above the plane, and Cl will be behind. This one goes from being R to S configuration. So the easiest way to invert stereocenters, in my opinion, is to simply swap two groups, and swap the groups that are above and below the plane of the page. So here's an enantiomer, and here's an enantiomer. And when we say they're enantiomers, what do we mean? Well, we mean to say that they are mirror images, and they are non-superimposable. Great. But you know, there's something else we could do. Since we have multiple stereocenters, what if we change one stereocenter, but not the other? Well, that opens up a whole new possibility. So, let's redraw this first structure, and let's simply leave the alcohol stereocenter the same, and let's swap the chloride. So based on what we said, okay, this has the S configuration, we redrew it the same. This was R, we swapped it, this should now be S. Well, what will this be? As it turns out, if you change at least one stereocenter, but not all of them, and we change one of two, these will not be mirror images. So this is a non-mirror image of that compound. However, it's non-superimposable because we have changed the stereocenter. Molecules that are non-mirror images and non-superimposable are called diastereomers. As it turns out, there's another possible structure we can draw. We've drawn the SR, the RS, the SS, and what we haven't drawn is the RR. So let's go ahead and look at this R. For R, we had the hydrogen up and the OH down. And for the R with the chloride stereocenter, we had the chloride up and the H down. So this is the RR. Now what's the relationship of these? So to go from the SS to the RR, we've reversed both stereocenters. These are enantiomers. And when I said both stereocenters, we've changed all of the stereocenters. Well, that's going to get us to an enantiomer. These two are enantiomers. This structure right here, the SS, is a diastereomer to this second structure because we changed one stereocenter, the OH stereocenter, but not both stereocenters. We left the chloride stereocenter the same. Likewise, this structure, and this is going to get ugly, these are diastereomers because we changed one stereocenter, the chloride, S to the R, but we didn't change the other one. The OH stayed in R. So you get all these relationships, and as long as you just redraw it and start swapping groups, you change stereocenters. As long as you change not all stereocenters, you will be in the realm of diastereomers. They're non-mirror images, non-superimposable. But if you change all the stereocenters, then you get enantiomers. We'll talk about the math behind this in just a second.